Yeah, thanks for having me here, and thanks for rescheduling my talk since I wasn't able to make it here in time. Yeah, O'Hare was shut down yesterday. I don't know who else had the problem. So I'm here on behalf of the CAGE collaboration, and in the last talk already, we went to quite different scales, and here we take it up a notch, where single particles in the simulation are have the mass of thousands of solar masses. That's what we need to do to simulate galaxy evolution. So the CAGE collaboration, that's me. I'm Ludwig Oser, currently working at Columbia. The PI is Ken Nagamine, who's actually now in Osaka, and the other members are Jerry Ostreicher, Thorsten Naab in Munich, Manisha, who sits here in the room, Greg Ryan at Columbia as well, and Renyu Chen from Princeton University. So, yeah, you heard the word inflation today as well, but here it has a different meaning. So what we're trying to do basically is to, it sounds daunting to simulate the whole Hubble time, so the whole evolution of the universe. We start more or less a glimpse after the Big Bang. So simulation, we start, we simulate roughly 13 billion years of evolution. So we don't simulate the inflation, but we start when the everything has settled down a little bit from more or less homogeneous initial conditions. And then we want to see how we can this evolve into the universe that we observe at the present day. So we have a quite good understanding what's happening in the Big Bang. Or we think we do have that. We know how the universe looks today in the in our neighborhood. And now we have to fill the gap. How do we get from those more or less homogeneous initial conditions to the diverse galaxies that we find at the present day? So to understand that, we need to take into consideration a lot of effects. I'm not going to go through all of these, but the understanding that we have is that, like I said, at the early times, the matter is more or less homogeneous distributed, and by gravitational collapse, we form structure. First, we do this with dark matter, because there's just much more dark matter than baryons in the universe. And in the gravitational potential wells that are built by the dark matter, the gas will follow, and the gas will ultimately radiate away its energy. It will cool, it will form stars, and those stars will form galaxies. Now, this sounds pretty simple, but as we find out, it's not that simple. So if you do it that simple, one of the main concerns that you have is overcooling. That means that just by looking at the total amount of hydrogen that we have in the universe and how well hydrogen is able to cool, we should form a lot more stars. But it turns out that galaxy formation overall is a very inefficient process. So at the present day, only very little of the mass that we have in baryons in the universe is actually formed in stars. So we have to consider various forms of feedback that prevent this cooling. So there's supernova feedback, which is by exploding stars, which give big energy into the gaseous form, or by supermassive black holes in the center of those galaxies. And all those effects will eventually prevent further cooling and delay star formation. But to simulate all this, what we start with is we forget about all this, what I just told you, and we start with a simulation that is purely collisionless and does only consider gravity. So this is a slice through the simulation. It's a box of 100 megaparsec side length, and we simulate this for the whole time, for the Hubble time up to the present day. And we do this at first at homogeneous resolution. So all the particles in the simulation have the same mass. And when we evolve this to the present day, it doesn't look that nice on that projector, because in the beginning everything was just dark. We see that this filamentary structure is evolving, the so-called cosmic web. Along, you have some knots where possibly galaxy clusters are forming, but like I said, so there's no gas in the simulation. We only want to see what the large-scale structure formation in this simulation looks like. But what we find is that overall, yeah, it's not that nice to see here. The particles don't travel like through the whole box in the, during the simulation time. We find the structural collapse, but if we want to have a look at one of those structures, for example, we just pick one, and we look back where all these particles are coming from, it's still like a finite region that doesn't fill up the whole box. So what we can do is now rerun the simulation with the same volume. So we're still looking at a 100 megaparsec cubed box, but we're only putting particles of better mass resolution in the region where this one single structure is going to form. And this is what we are calling a so-called zoom-in simulation. So we move the structure then to the center of the box, and in red, this would now be gas particles, so particles that are allowed to collide, to radiate, to cool, and to form stars eventually. And around it, we have dark matter particles of increasing mass, the more we move to the outside, to represent the large-scale structure formation, because we need the gravitational forces that is exerted on our structure. We still want to have a cosmological simulation. So and now we rerun this again. We start at the same time that we did before, but this time we are considering all the effects of gas cooling and star formation, so that we're actually forming a galaxy. And yeah, so this was be where there was supposed to be a movie of this one structure forming. And this would be a so-called merger tree, so a graphical representation of how this buildup of the structure looks like. So we have the most massive progenitor. This is the present day down here. And all these little structures at some point fall into this main structure. So we merge this galaxy. This galaxy at the present day builds up out of a lot of smaller structures that at some point fall into the central structure. And there we can already see why almost no two galaxies look alike, because this is a very intricate formation history, and how exactly the mass is built up will have a significant influence of what galaxy you're actually going to have in the end. So what I'm trying to convey here is that although it's nice to form single galaxies, you'll never know the right answer. Even if they form on some relation that you predict, you never know how far your scatter should be like. So what we actually want to get is, we want to reproduce the statistical properties of the observed galaxies. So reproducing one galaxy doesn't tell you a whole lot about whether your model is successful. What you want to do is to model the statistics that we find in the observed galaxies. So a single simulation of such a structure won't help us. So what we did was a couple of those. And up to that point, it was the largest sample of such zoom-in simulations. And we went up to structures of 10 to the 14 solar masses. So that's the total mass of the whole structure, not of the galaxy in the center. And we were successful in showing, for example, this is one plot from a scientific paper that we published. And for example, showing the evolution of sizes of those galaxies. So what we see here is the mass of the galaxy plotted against their size at different redshifts. So this would be the present day relation, the observed one in the black dashed line, and all these colorful dots are our galaxies at different redshifts. And on the right hand side, it's again the sizes, but now against redshift. And again, we see the observed relation here. So we can reproduce this evolution. It's quite nicely, but with our 40 galaxies that we have here, it's very hard to compare, for example, the scatter that we find in the observed relations. So large-scale galaxy surveys have on the order of, well, the SDSS, which is a survey of local galaxies, it's 1 million galaxies. So if we want to compare statistics with 40 of those, we won't get far. So what we need to do is we have to improve on the statistics. And there are two approaches to that. First of all, you could just take the whole box that I showed you in the beginning and just fill the whole box with gas particles and run it to the present day, and you will build thousands of galaxies in those. But astrophysical codes have some inherent problems, in load balancing, and you will run into trouble if you want to do this at a sufficient high resolution. So the other approach would be to do those zoom-in simulations like we did, but to do thousands of them, like ensemble computing. And that's, you might have guessed, is what we are advertising. So, of course, this comes with a couple of pros and cons. So the disadvantages of that is that in the end, you only have gas in a finite region in your simulation box. So you won't be able to shoot like sidelines when you want, for example, look at metal absorption lines along a sideline through your simulation box. You won't be able to do that. You won't have any long-range baryonic effects, like one galaxy sending out radiation and ionizing another galaxy that's far away. But for the foreseeable future, no full box simulation is going to do such ray tracing effects in a feasible amount of time. This should actually read pros. What you are able to do with the zooms is you can reach a much higher resolution for a single galaxy. And resolution is very important to model effects like supernova feedback correctly. And most of all, when you do a full box simulation and you choose a model for example, what your effects of supernova should be on your interstellar medium, you're stuck with a model for that simulation. And the zoom simulations, this way this enables us to test different models, to tune the parameters and see what the effects on the galaxies that we simulate is. So we did a couple of scaling tests. Of course, we wanted to show that this is something that works and that actually makes sense. So this is for full box simulations when you a weak scaling test. So we increase the problem size as we increase the number of cores. And overall, the scaling, like I said, our astrophysical code doesn't do that well. And I'm not going too much into detail here. But what we are basically doing is dividing this into problems that can run concurrently. So it's actually becoming an embarrassingly parallel problem. So you're not running a single simulation, you're running literally thousands of them. So the theoretical scaling should actually be that perfect, that with the number of CPUs, you just can run more of those problems. And what we want to show is that, of course, you're running the full volume all the time, but you're spending most of your computational time actually in this high-resolution area, because you only have most of the particles are actually in the structure that you're following. So the overhead for resimulating the background over and over again is actually negligible, and it might be trivial that, like I said, when it's an embarrassingly parallel problem, that the scaling becomes perfect, but it wasn't obvious to us in the beginning that on Blue Waters you don't run into any bottlenecks when you just spawn thousands of MPI jobs from your own scheduler. So that's what we are doing. We have a catalog of these dark matter simulation that we ran in the beginning. So we look for structure there at the present day. We find on the order of 40,000 objects that are more massive than 10 to the 10 solar masses at the present day, so possible candidates for resimulation. And we automated the process of picking those and generate initial conditions for all of those, if you like, and then according to its size, assign a number of CPUs that you want to run them on. So the scaling test that we did for that is rather simple setup. So what we did, we choose 4 objects, and here you see the initial conditions if you put them in the same box. So we have this with the 4 in them at the same time. It's what in the following slides is called the combined run. And then, of course, you can divide this when you only have one structure, and all the other structures would then be only poorly resolved by only dark matter particles. And then you can run them concurrently. So if you do this and you use the same number of CPUs for that, you already save a little bit of time. So this is the combined run. This shows wall clock time, so the shorter the better. and this is the 4 concurrent runs, and this already saves you some time. But the real speed up comes from that, of course, we don't need to use the same number of CPUs this way. So instead, so if we now increase the number of CPUs by a factor of 4, the combined run doesn't actually save a factor of 2 here. But of course, increasing the number of CPUs by a factor of 4, we can run those concurrently instead of sequentially. So what you're comparing here then, of course, would be the full bar here and only the simulation that takes the longest out of the 4. And this already, you see, takes only 40% of that time. So just by dividing this into separate concurrently running simulations, you save a huge amount of time. So this is still a low resolution run that we did here, but we ran this for the whole time. This is the resolution that we're aiming for, but we only run it for not for the whole simulation time, but we get similar scaling at different resolution levels. Now this plot you have to take with a grain of salt because it's extrapolating results from smaller simulations up to very large numbers, and there's a lot of theory going on in this one. What I'm trying to show here is what box size you would be able to calculate in a given amount of CPU hours. So this is volume of your simulation box, this is CPU hours, and we are extrapolating our weak scaling results for the whole box on the top here, and we are aiming for a resolution that would enable us to resolve the effects of supernova, in our opinion, sufficiently. And you find that, I mean, with 100 megaparsec cubed box, you're already running into unfeasible large CPU hours that you won't be able to do. So the hacker line, what we are assuming here is that you would be able to, to divide the whole box into all its single structures. And of course, depending on the box size, this is a different problem. So what I mean by that, I'm sorry, it's complicated to explain. If you just form a single structure in your box, you won't be able to divide it just in two. You only can divide structures that are gravitationally bound. And what you find is that the universe is very homogeneous on very large scales. And that's why this becomes parallel to the line that shows the scaling if you would actually be able to divide the box into single boxes that all have the same mass, disregarding that it's not gravitationally bound structures. So on very large scales, the universe is homogeneous, and actually you can divide it into substructures that look self-similar, and that's why this becomes parallel. And what we find is that with like 0.1 gigahours, we would be able to simulate the full box of a cosmological volume, but of course with the hacker approach, in contrast to the full box, you can always just leave out structures. If you just leave out maybe the most massive ones, you save a huge amount of time, and you would still be able to run the whole thing up to redshift 0, whereas at the full box, if you run out of time, you won't be able to simulate it up to the present day. So since I'm running out of time, just run through this. The outlook, right now the code that we're using is the SPH code Gadget, is a pure MPI version. We would like to implement the hybrid approach that is often mentioned at the supercomputing conferences. And we are also still missing some of the physics that we want to put in. I didn't talk about that at all right now. So the conclusions, I leave it just up here since I'm running out of time. Thanks.